Namaskar. Welcome to Divine Chemistry. I am Divyashri. So in the previous video we have learned about hybridization, and in this video we will be learning about some common types of hybridization and how to predict hybridization. Because if we know how to predict the hybridization, then it will be easier for us to determine the shape of a given molecule. So let's begin. So here it is the summary of some common types of hybridization with shapes and examples. So please note one point that you don't have to pay much attention towards the examples, because you don't have to by heart it, and we will obviously learn how to calculate or how to find out the hybridization in the coming videos or in the coming slides. So firstly, here you can see type of hybridization, atomic orbitals involved, representing directions of hybrid orbitals formed along with bond angles, shape of the molecule, and then lastly the examples. So firstly, sp hybridization. As we have already learned, it is formed by one s and one p atomic orbitals. Now the angle between the hybrid orbital formed is 180 degree, and it can be represented like this. The shape of the molecule will be linear, and here are some examples like barium chloride and ethene, etc. Secondly, sp2 hybridization. We have also learned about this. Here, since it is sp2, one s orbital and two p orbitals are involved. This is the representation of the hybrid orbitals. Angle between them is 120 degree, and the shape of the molecule is triangular planar. The very common example is PF3. We will learn about it. Thirdly, sp3 hybridization, one s orbital and three p orbitals. The shape is tetrahedral, and one common example is methane. Fourthly, dsp2 hybridization. Since it is dsp2, one d orbital is involved, one s orbital and two p orbitals are involved. Here you can see that the x square minus y square orbital is involved. The shape is square planar. Examples are given here. And number 5th is sp3 dehybridization. Here one s orbital and three p orbitals along with one d orbital is involved. The shape is trigonal bipyramidal. And one more thing here to notice, that the shapes will be much more clear after reading the VSEPR theory. We will be covering this the theory in the coming videos, because from that theory, the valence shell electron pair repulsion theory, we will know how to determine the shapes of the molecules. So we will learn about the repulsions and the shapes resulting from it. Here you can simply just read about the shape of the molecules resulting after the given hybridizations. Number 6 is sp3d2 or d2sp3. This hybridization, one s orbital, three p orbitals and two d orbitals are involved, and the shape is octahedral. And lastly, sp3d3 hybridization. Here one s orbital, three p orbitals and three d orbitals are involved, and the shape will be pentagonal bipyramidal. So please note this point, that this chart is not to by heart, but it is just to understand how we can determine the orbitals which are involved by knowing the hybridization. And after knowing the hybridization, we will slowly learn about the shapes of the molecules, how they are formed, or why the shapes are like that. We will gradually learn about it. So now, since we have learned a few things about hybridization, now it's our turn to know how to calculate the hybridization, because it is not possible always to by heart the hybridization of the given molecule. So we will definitely have to know how to calculate the hybridization. So here is a very simple formula. Predicting hybridization. Calculate the number of hybrid orbitals x to be formed by the central atom as follows. Now please note this point, that we will, while finding the hybridization of a given molecule, we always find the hybridization of the central atom. So the hybridization of the central atom, we commonly refer it as the hybridization of the given molecule. Actually, it is the hybridization of the central atom which we will have to calculate, and after that we can determine the shape. So the formula is x equals to half of number of valence electrons of the central atom plus number of monovalent atoms or groups surrounding the central atom. Monovalent atoms or groups means the groups or atoms which are attached to the central atom and they have a valency of 1. When the valency is 1, we call it as monovalent atoms or groups. Minus charge on the cation plus charge on the anion. So simply we can say like this: X equals to half of valence electrons of the central atom plus number of monovalent atoms attached to the central atom minus, if there is positive charge, then you can then you have to minus that particular positive charge, or if there is negative charge, that means if it is an anion, then you have to add the number of negative charge present on the given species. So by calculating X, we can tell about the hybridization. For example, if X equals to 2, we can say that 2 orbitals are involved, so the hybridization will be sp. If the value of X is 3 orbitals are involved and the hybridization will be sp2. If the value of X is 4, that means 4 atomic orbitals are involved in the hybridization and the hybridization will be sp3, and so on. Now let us see some of the examples. Firstly, it is given as carbon dioxide. So if we want to find the hybridization of carbon dioxide, then first we have to calculate the value of X. So as we know, X equals to half of valence electrons of the central atom. Here central atom is carbon. Since carbon has a valency of 4, so here we have written half of 4 plus. So why we are writing 0? Because there is no monovalent atoms. As we know, oxygen is divalent. Since there is no monovalent atom, we don't have to add anything. So here we are simply representing it as 0. And since it is a neutral species, it is not a cation, neither an anion. So we don't have to add or subtract anything. Simply it is 4 by 2, that is 2. Since the value of X is 2, so the hybridization is sp. That means carbon dioxide is sp hybridized. Secondly, we can also see BF3. Here the value of X half of, since the number of valence electrons of boron is 3, so we are writing half of 3 plus 3. So why we are writing plus 3? Because we have to add the number of monovalent atoms. Here since number of monovalent atoms is 3, because fluorine has a valency of 1, so it is a monovalent atom. So we are adding 3, and since it is a neutral species, neither a cation nor anion, so we don't have to add or subtract anything, and thus 6 by 2 equals to 3, and thus the hybridization is sp2. So similarly, we can calculate the hybridization of any given species. Please practice to calculate the hybridization, because it will be easier for you then how to calculate the hybridization of the given species. And that's all for today's video. Keep practicing how to calculate hybridization. It will be much helpful in order to determine the shape of the given molecules. And thank you so much for your patience, and thank you so much for listening to me. If you like the video, please give it a big thumbs up. And yes, please do subscribe to the channel. I'll be much happy for that. And yes, do share the video with your younger ones, your younger brothers and sisters who are interested in chemistry. And stay at home, stay safe, take care. Thank you.